So last time we started from the zeroth law, and then we went through the first law of thermodynamics, which is the conservation of energy. And we talk about the difference between heat and work, although all of them are in the dimension of energy, but they are actually a very different form of energy. So again, if you're considering heat, it means that it will generate some random motion in the surroundings. But if you're dealing with work, it means that you can perform a uniform motion. For instance, you can expand the air and then move the piston such that you can do something meaningful. So heat and work are both energy terms, but they are in very different formats. So this week we will talk about the second law of thermodynamics, which is related to the increase in entropy. So first of all, we have to define what entropy is. Before talking about the second law, here is a part of the paragraph from the book of Peter Atkins. So he mentioned that the second law is related to the liberation of the human spirit. So he was a chemist. He is still a chemist, and he teaches general chemistry. I think at I don't know, Cambridge or Oxford. So here he mentioned that when he gave lectures on thermodynamics, which is this course, to undergraduate chemistry audience, and he often began by saying that no other scientific law has contributed more to the liberation of the human spirit than the second law of thermodynamics. So he hopes that, like the audience, the readers, will see in course of this chapter, which is the chapter about second law, why he took that view and perhaps go so far as to agree with him. So to be short, the reason why he thinks this is related to the liberation of human spirit is because the second law actually set up some boundaries about what you can and cannot do. For instance, we know that there's no perpetual machine, which means that you always need some input of energy in order to do some work. So you cannot get free energy for free. You always need to spend something to get something. And that's the spirit of the second law of thermodynamics, and it is also related to the liberation of the human spirit, because you know like what you can do, what you cannot do, and you are not God. But of course, from a scientific point of view, a general statement of the second law is that the entropy of the universe increases in the course of any spontaneous change. So the universe, you can consider, of course, the universe that we're saying right now is probably the whole universe. And of course, the entropy of the universe is the entropy of an isolated system. So again, if you still remember, the isolated system is a system that having no exchange of energy and no exchange of matter with outside. And of course, the universe is the largest system we know so far, right? We don't know if there's anything outside this universe. Perhaps there is, but we don't know. So this universe can be considered as the largest isolated system. So within this isolated system, the entropy can only increase. And eventually, this increase of entropy will gradually saturate it, and the universe will become a very uniform system. So this statement is very important, depending on what are the systems that you are dealing with. For instance, if you're dealing with an open system, then the entropy of that system can increase or decrease, depending on if there's any energy exchange, right? I believe that you learned that during your freshman year. So the system that we're talking about is very important. The isolated system will give you the second law of thermodynamics. And before talking about entropy, let us look at internal energy again. So internal energy, as you learn from the first law of thermodynamics, it's a quantity of energy that a system possesses. For instance, like last time when we talked about the ideal gas, I mentioned that the internal energy of an ideal gas, we'll encounter this again very soon. Well, sorry. For an ideal gas, the internal energy can be expressed like this, as you probably already know. It is only proportional to temperature. So it's a function of temperature. So a system of ideal gas and the quantity of its energy can be expressed by this U, this state function. So as long as we know what the internal energy is, for instance, for an ideal gas system, we know the temperature of the system. So that's the reason why we call this a state function, because once this is fixed, then the state of the system is also fixed. Okay, so we will go through this in detail when we look into the first chapter of the textbook. But we already mentioned this last time. So internal energy is a quantity of energy of the system possesses. And to talk about second law, we have to talk about the definition of entropy. And qualitatively speaking, entropy is, say, the quality of that energy. So, for instance, when we talk about an energy exchange in between the system and the surrounding, and we want to know, like, the quality of this energy, is it low or high? At this point, this is still pretty vague. What does that mean? Like, this energy flow has a high quality or low quality? But later in chapter 3 of the textbook, we will see like how this definition works. But at least right now, we can define that if there's a low entropy, then we have a high quality of energy. In contrast, if the entropy is high, then the quality of the energy is low. So we know that entropy, like when you were in the freshman year, you know that it's a degree of, for instance, randomness, 乱度. It's a measure of that randomness. So if the entropy is low, it means that the randomness is low. So the motion, for instance, of the particles in the environment is more ordered. So it means that the energy involved is having a higher quality. So this is also related to our understanding of the difference between work and heat, right? If you're doing work, like I mentioned last time or just earlier, that you're doing an order, doing an order work, or pushing the atoms or particles in a uniform motion. So the energy of that is having a high quality because you are doing something that is meaningful. However, if you're dealing with heat, the entropy is high because the atoms or the particles are moving around randomly, so the quality of that energy will be low. And actually, we can define quantitatively what this entropy is. So here is just a qualitative description of what entropy is. And to talk about the definition of entropy, we also have to introduce heat engine. A heat engine, or sometimes called steam engine, because at the very beginning when people invented this engine, it was driven by steam. We're using this motion of steam, which is a bunch of particles, or gas particles. We use steam to drive the force. So we also call this steam engine. So this alarm, we can ignore that. So the steam engine is actually the heart of the spirit of the second law. And we will see that later, why the steam engine is so important and why we need such a mechanical definition of second law of thermodynamics. And here is an example of a steam engine. This is what you will see very frequently when we talk about the materials in the textbook. This is a cylinder, and we have a piston. So a cylinder and a piston in combination is a very simplified version of a steam engine. Although in modern days, for instance, in a car or in a power plant, you have more complicated steam engine or heat engine. But this is probably the most simplified version of that. So you have a cylinder, and you have some gas inlet and outlets, and you have a piston that you can compress the gas inside. You can compress it, and you can release it, such that you can do cyclic work. So you can keep compressing and releasing the pressure or the air inside, and you change the volume and the pressure of the gas within this cylinder in a cyclic form. So you can do this back and forth. And that's also another feature of heat engine. You can do this more than one time. And if you look at this figure here, you'll see the curve or this circle here, or this cycle here. It means that the position, the horizontal axis, is the position of the piston. And in analogy to the volume of the gas inside the cylinder. And on the other hand, for the vertical axis here, it marks the pressure. It means that when you compress the gas molecules inside this cylinder, the pressure will go up, right? So if the position of the piston is here, you'll see that the pressure of the gas inside the cylinder will go up. And through this process, when we do this, this heat engine can do work to the outside, or in contrast, on the contrary, you can also do this in reverse. You can enforce work into this piston or this heat engine, and then convert heat from one side to the other. So that's the reason why we have heat engine. But if you reverse the process, then you have a cold engine. For instance, the AC that we're running right now, the air conditioner we're running right now, is the reverse. Is the reverse of heat engine. We'll see more examples later. And one of the most important engine, or heat engine, is proposed by Carnot in 19th century. And this Carnot engine is probably one of the, probably the only one that you'll encounter in the near future. There are some other types of engine which involves different kinds of cyclic process, but this is probably the most important one. And this Carnot engine is a imaginary engine. So there's no real engine that can be acting like Carnot engine. So it's an ideal case. Like what we're dealing with is ideal, we have ideal gas. But in reality, we know that there's no system behaving like an ideal gas. So the Carnot engine is the same. It's you can say that it's an ideal engine. And it is also having the maximum efficiency. So this is the reason why the second law of thermodynamics is important. At the very beginning, when people started inventing different kinds of engine, then the scientists started to think about the possibility of maximizing the efficiency of such tools. For instance, if you have a car and you want to reduce the consumption of fuel, and you have to maximize the mileage that you can go, right? So you have to measure how many gallons that you have to put in order to go 1 mile or 1 kilometers. So it depends on the design of the engine and the design of the car. But thermodynamics, especially the second law of thermodynamics, at the very beginning of the invention of that, it tells you that the maximum efficiency of any kinds of engine is this formula. So as long as the temperature of the sink and the temperature of the source of the energy is fixed, then the efficiency of that is fixed. And this is the maximum that you can get. This is still very abstract right now, but if we look at the design of a heat engine or any kinds of heat engine, you can reduce that to this plot over here. You extract the energy from something hot, and then you transfer that heat into this engine, and this mechanical thing will do something to the environment or to the things that you want to drive. For instance, we want to move our car, and we extract the energy from the fuel that we put in, and then we convert that heat into some certain type of work that drives the car. And we definitely will have some heat being lost to the environment. And later we'll see that this part is always there. It is impossible to have a total conversion or a complete conversion from the heat over here to the work. So there's impossible to get the efficiency to 100%. It's really hard. It's not entirely impossible, but it's very, very hard to do that. So this heat engine showing here is represented by a circle. It doesn't show like how this system or how this machine will work, but theoretically this is what we typically will draw. We have a hot reservoir to supply the energy as a form of heat, and we have this mechanical thing to transfer that or to convert that into work, and some of the heat or some of the energy will be transferred to the cold part of the environment. So at least in this book, they call this the hot part, the hot reservoir, which means that there's a fixed temperature. For instance, the largest heat reservoir or hot reservoir for the solar system will be our sun. That also applies to the Earth, right? If we're dealing with Earth as our system, then the largest, the major heat reservoir, the energy source of the Earth is our sun. So we know that the temperature of the sun is fixed. So from that, you can extract the efficiency of probably the best heat engine of the system by putting the temperature of the sun over here, right? And the coldest part on Earth, you can put that into the T-sink here, then you can extract the efficiency. But for most of the time, if you're dealing with the heat engine, on the Earth, if your source is not from the solar power, the temperature will be a different number. For instance, if you're driving a car, let's say if you burn the fuel and the heat reservoir can give you a temperature at around, say, let's say T hot is a 400 Kelvin. And the heat sink, the environment, like the outside of the car, let's say is 300 Kelvin. Then the efficiency will be will be 1/4. So if you're dealing with, for instance, most of the systems on Earth, it's very typical that the maximum efficiency that you will get is like 20 or 30%. So that's sort of the thermodynamic limits for your heat engine. So it's really hard to get a heat engine that will give you almost 100% efficiency. Okay, so that's what thermodynamics tells us. And therefore, over here, we'll see that the efficiency originally is defined as the ratio between work and the heat converted, transferred, from the hot end to the heat engine. So the QH here means that the heat transfer, from this hot part to the heat engine. And a part of the heat will be converted into work by this engine. So this is the output. So the output over input, that's how we define the efficiency of the system. And it turns out that due to the conservation of energy, because we know that this QC, which is the heat transferred to the cold end of the environment, if you add this and this part, these two, the sum of these two will be the original input. So this is the conservation of energy. If you do that, this is the resulting efficiency, because W is QH minus QC. So eventually, later we'll see in this semester that these three factors, these three numbers, can be converted into the temperature. So we can further simplify this into this form. So eventually, the heat engine efficiency is only related to the temperature of the sink and the temperature of the source. So the temperature of the source is the temperature of the hot end, and temperature of the sink is the temperature, of the cold reservoir. So the efficiency can be defined like this. And this is at the very beginning of how people started looking into the heat engine and the second law of thermodynamics. So generally speaking, there are three statements of the second law. The first two, which were proposed by William Thomson, later named Lord Kelvin, and that's the reason why we use the temperature scale Kelvin. It was named after him, William Thomson. His statement of second law is that heat cannot be completely converted to work. So we already know that when I talk about this figure. So is it impossible to have QH equals to W, because there must be some dissipation into the cold part. So this description is represented by the figure here. This is also taken from the Peter Axen's book. So if you have a very non-ideal heat engine, and it can just convert the heat completely into work, it means that you are having a perpetual machine. Perpetual machine is so 永动机, okay, it is impossible to have a complete conversion of heat into work. Then you don't have to. It means that you don't have to input anything. Then you can pump heat from one end to the other. So it ends up that this statement is the same as Clausius' statement of second law, and this is what I just mentioned. Like, heat will not spontaneously go from a cold object to a warm object. So imagine that you don't have to put in any work, and the heat will just flow from the cold end to the hot end. Then you have a perpetual machine, right? You don't have to do anything. But we know that it's impossible. But otherwise, we don't need to build any power plant to cool down, our classroom, right? We can just turn on something, and then we don't have to consume any energy, and then we'll be very cool in here, and it will be hot outside. So in order to do something, for instance, transferring heat from this room to outside of this classroom, we always need, for instance, air conditioner. And we know that air conditioner will consume energy in the form of electricity. So Clausius' statement is essentially the same as Wilhelm-Thomson or Lord Kelvin's statement. Another more general statement, which typically we will use, is that the entropy of an isolated system increases. Of course, from the very first two, you'll see that there's no definition of entropy, right? We're just talking about heat engines. And we have very mechanical explanation of how works are done and how heat will flow. But we don't see any definition of entropy yet. But it turns out that if you use these two statements together, and if you introduce the definition of entropy, it ends up with this very simple statement. The entropy of an isolated system will just increase. Okay, so this is what we will go through in details when we talk about, when we started looking into our textbook. But I think it's good that you just have a brief understanding here at the very beginning that these three are the same statements in essence. So in Peter Atkins' book, he stated more in details that Wilhelm-Thomson's statement is that no cyclic process is possible in which heat is taken from a hot source and converted completely into work. So that's the same as what I schematically show here. But more importantly, he talks about the cyclic process. If you still remember, when we talk about how the heat engine works, we say that we have this cyclic process. The piston will move back and forth to compress and release in a cyclic way, such that we can do continuous work. And therefore, for heat engine, we typically have cyclic process. So that's the reason why he specifically stated this as a cyclic process. But there's no cyclic process that will convert heat completely into work. You always will have some loss of heat in terms of dissipation into the environment. And for the second one, heat does not pass from a body at low temperature to one at high temperature without company change elsewhere. So if you have heat, transferring from low temperature part to high temperature part, you will always change something else. For instance, if we do something like this, if we pump energy in a form of heat from cold end to hot end, like we try to keep the temperature down over here in this classroom, then it means that we're introducing, for instance, entropy to the outside world because we're keep dumping heat into the universe. So we're keep increasing the entropy outside, although we're reducing the entropy here. Right? So you're always changing something if you want to transfer heat from cold end to hot end. The reverse is the opposite. If you want to transfer heat from hot end to cold end, then we know that this is a spontaneous process, right? We don't have to spend any work. And we know that eventually, when these two systems are in contact with each other and when the heat is flowing from hot end to the cold end, eventually they will have the same temperature. And this is related to the zeroth law of thermodynamics, that when the system are having the same temperature, it means that they are in thermal equilibrium. Okay, so the opposite is different from what I just mentioned. If we want to pump heat from cold to hot, we always need to spend some work, or something will change outside this system. And the general statement is that the entropy of the universe increases in the course of any spontaneous change. So it means that as long as the time is moving forward, the universe, regardless, it's this whole campus or the whole universe that we're talking about, the entropy of it will always increase. It will always increase because we know that the time is moving forward. It's not going backward. So in order to go back in time, we have to break the second law of thermodynamics. So that's another revelation for the human civilization, that you cannot go back. Okay, you cannot go back. You can always go forward. Okay, so the equivalence that I mentioned earlier between these two statements, in order to verify that, we have to combine the two engines together. For instance, imagine that you have an ideal engine. Sorry, not ideal. You have a perfect engine that is unrealistic, that can completely transfer heat into work. And if you combine that with a regular engine that will transfer heat from cold end to hot end, then if you add them together, this will become an engine that can just pump heat from cold end to hot end. So it means that the statement from Kelvin is equivalent to the statement of Clausius. On the other hand, if you do this in a different way, if you have the heat directly flowing from cold end to hot end, and then you put another heat engine over here, then you'll see that it will completely transfer the heat into work. We will see more detail on quantitative analysis when we go through textbook. But please keep in mind that these two are equivalent. And to prove that, we can just combine these two together. Sorry, not combine these two. Combine each one of them with a regular heat engine. And then the overall heat engine will be just acting like the other one. So it means that these two are the same as each other. And so it turns out that to define the quality of that energy, Clausius, so he started from the concept of heat engine. And again, these are just based on classical thermodynamics. So we don't know like the microscopic description or how the molecules will work. But just starting from the heat engine and the observation from the experiments, he suggested that we can define the change in entropy or the change in the quality of that energy as the ratio between heat supply reversibly to the temperature. Okay, so it means that let me see if I have it here. Okay, so the formula is like this. The change of entropy ds or delta S is delta Q reverse. So this is the heat during the cyclic process of the heat engine. And the reason why we call this QREV, or we have a subscript here as reverse, is because when we want to do quantitative analysis, typically we have to rely on the process being a reversible process. remember like last week when we talked about the definition of processes, we have irreversible process and reversible process. And most of the time, if we want to have quantitative analysis, we have to restrict ourselves to the reversible process. So if the heat, the delta Q, is related to this reversible process, then we can define the entropy like this. It is the change of this heat over the temperature. And this temperature is the temperature of the environment. Okay, the temperature of the environment. So again, the change in entropy is heat supplied reversibly, which is, sorry, let me go back. This part, the heat supplied, from the hot end. And the temperature, will be the temperature of the reservoir. So this is the definition of the entropy, or quality of that work, quality of that heat in terms of classical thermodynamics. For statistical thermodynamics or statistical mechanics, we have to use Boltzmann's formula. Last week we talked about Boltzmann. He was the, let's say, the creator of modern statistical thermodynamics. And the definition of entropy from his formula is K times log W, or log omega. The next slide. So here are the definition or the expressions from Peter Atkins' book. But these are more general expressions that we will see in our textbook. That delta S or ds is delta Q over T. And for Boltzmann, a statistical approach, the entropy is defined as an absolute number. So it's not a delta value. It means that we can define entropy as an absolute quantity. So it's not just the difference that we can extract. We can also extract as absolute value. Okay, so S equals K times log omega, and this K is the Boltzmann constant. So typically you can say it's K subscript B, and this omega is the possible combinations of the configurations. Let's say this is a number of possible configurations. For instance, the systems might have, a lot of particles, and these particles can arrange, in many different ways. So each unique configuration or each unique arrangement can be counted as one possible configuration. So imagine that if you have a lot of particles, say the particle of numbers is, say, 10 to the 23, then you have many different possible configurations. And that is actually the reason why, at the very beginning, they decided to put a log in front of it, because we know that this number will be very big. And it turns out that putting a log in front of it has some certain physical meanings. And so this is a good measure of how many possible configurations in the system will affect the quality of the energy in the system. So for instance, like if you have this many configurations, taking a log here, you'll see that the order of magnitude for this quantity is only like 20, 23, or 30 something. So although this number is really big, but this factor won't change that much. So this is sort of a good physical quantity to define entropy. Okay, and the Kb here is also important because this is where the Boltzmann constant comes from. And when we talk about statistical mechanics in detail, we'll see how this links to the definition of say, temperature. Remember that when we talk about the population inversion last week, we say that the population distribution will determine the temperature of the system, because it depends on like how many particles are in higher energy levels and how many of them are in, for instance, in the ground state, and the relative numbers, of these two states, or high energy state and low energy states, will determine the temperature, and that factor is also related to Kb, if you still remember that. If you forget, please go back to the last lecture. So Kb is also related to entropy. So we can see that second law of thermodynamics is the connection will bridge the classical and statistical thermodynamics. So this formula is very important. Although in textbook, this is probably only part of it, because in the thermodynamics of materials, I guess the classical thermodynamics is more important. But in the future, if you're going into more physical science research, you'll encounter this more often. So this is a summary of what we've covered for the first 2 weeks. First of all, the zeroth law. The temperature as the measure of the thermal equilibrium, which means that if you have 2 or 3 systems, and if they are in thermal equilibrium, then we need a measure to tell us that they are in thermal equilibrium, right? And this measure is temperature. So for instance, we are making some, this maybe is not a very good analogy. Anyway, forget about it. I think you're smart enough to understand this. Just the temperature is a measure of that. But if you're looking at a statistical mechanics, we know that it's the distribution of the particles among different energy levels. If the distribution is the same, then we'll say the temperature is the same. So the temperature is actually a measure of equilibrium. The next one, the first law, states the conservation of energy. So the first one, the zero law is about temperature, and the first law is about energy. And we already know that the statement is the heat equals to the internal energy of the change of internal energy of the system and the change of the work of the system. So I guess I want to review that again. That if we have heat going in and out to the system, and the internal energy is a state function, so it's the measure, it's the state function of the system, so it's not related to what's going on outside. So if we have heat coming into the system, then the internal energy should increase, right? If there's no work being done here. If we have a positive delta Q or dQ, then we should have positive change of internal energy, because we're dumping heat into the system. So the temperature of the system will rise, and internal energy will increase. However, if the system is doing some work to outside as well, then this will also change. For instance, if we have a positive work, it means that, let's say, if we have positive work, it means that the system is doing something to the outside. So overall, these two things adds up to be the heat. And like I mentioned last time, there are many different kinds of definitions. Sorry, just 2 different kinds of definitions. So you will see this as a positive sign or a negative sign from different books. So every time you have to be careful, like what formula that you have to use, is it plus sign or minus sign? Or sometimes if you want to just be careful about this work, you have to define the direction first in order to make sure that you are using the right sign. But whenever you have doubts, just look at the first chapter of this book. I think it's the first chapter or second chapter. Then it has a clear definition of what you should use. But I believe in this book, in this textbook, it's the plus sign. So this is what typically I'll memorize. And today we talk about the second law, which is related to entropy. So again, the 0 law is about temperature, first law about energy, and the second law is about entropy. So the entropy of an isolated system will always increase. So of the universe, the entropy of the universe will only increase. So if we're dealing with this kind of system, for instance, this is a closed system, because we know that there is some energy exchange between the surrounding and the system. So the entropy change of the system can be negative. So in this case, the entropy change of the system can be negative. Because this is a closed system. And we allow energy exchange. However, if you're dealing with an isolated system, let's say you have a wall, and it will isolate any kinds of energy exchange, then for this one, it is always greater than 0. If your system is isolated. And that's the reason why we say the entropy of a universe is always increasing, because the boundary of the universe is the largest boundary that we know of. There's no outside. So we definitely know that the entropy of the universe will increase. The third law, which I won't cover in detail this time, is related to the definition of absolute 0. The temperature, if we can go down to 0 temperature, what will happen? And it will link the definition between temperature and entropy. So absolute 0 and the absolute measure of entropy will converge when you go down to very, very low temperature. Only when you cool down a perfect system down to absolute 0, you can get an absolute 0 of entropy. And the reason why that's the case is because we know that from the definition of Boltzmann that S is KB log omega. And if you consider a bunch of particles, we know that if you cool down to low temperature, these particles are no longer moving around, right? You cool it down. So those particles will gradually lose kinetic energy. So they will be frozen. So once they're frozen, ideally, in the perfect crystal case, this will become 1 when temperature is going down to 0 Kelvin. right? So in that case, S is 0 as well, by the definition, because if you put 1 here, log 1 is 0. So this is related to the third law, like whether or not it is possible to get omega equals to 1. We know that actually in some systems it's impossible to get only one configuration, even if you cool down to cryogenic temperatures. So it depends on the systems that you're dealing with. Okay, so I think these are the summary of what the laws are. So whenever you forget like what these thermodynamic laws are about, please just come back to this slide. And starting from next class, we'll start from the first chapter of this book. So I hope you get this already. Okay, let's stop here. So starting now, we're going to go through the textbook. So I hope you have this already. And so what I have right now is the 6th edition, which is not that different from the 5th edition. I saw some of you have the last version, except that some problems I think some new problems were added to this new version. But if you're still using the last version, I think it's fine. Yeah, they're not that different. And basically the slides that I have will be similar to what you had probably your closer to the last version, because in the new version of this textbook, I think another author added some new parts, but they are not that related to what we're going to teach. So if you still have the last version, I think it's fine. So the first chapter is sort of like a rephrase of what I've already taught, the introduction and definition of terms. For instance, what is a system, what is the state, and what are the energy terms that you will encounter. So 1.1 is the concept of state. Again, the system is matter that is the subject of the thermodynamic analysis. And we've seen this kind of graph over and over again, that a system may contain many phases. So it could have just one phase, or you could have two phases. It does not really matter like how many phases you have, as long as it has some certain boundary. And the most commonly seen system is, for instance, a piece of, for instance, a metal. And we know that there's a clear boundary between this metal and the air. So there's a boundary that can be well defined. That is probably the most important thing for a system. And inside the system, it can be a bunch of molecules. It can be gas molecules, can be liquid, can be solids. It does not really matter. And more importantly, outside this system is what we call surrounding or surroundings, depending on how you define it. And the surrounding plus the system, like we talked about last week, is what we call the universe. So the universe is the whole thing combined together. And of course, for a system, you can transfer heat into it. The heat can also go outside. And you can also do work onto the system, and system can also do work to the outside. So you have work done by the system or done onto the system. And depends on the direction of the work. So when we talk about system, remember this plot is important. And the state of the system is microscopically, the atomic arrangement and the energy associated with the system. So it means that there are several different ways to define a state. You can say it's a certain configuration of all the molecules or all the particles within this boundary. For instance, when we use Boltzmann's formula, we talk about this omega, right? This is the configuration number or the possibilities that those particles inside the system can arrange. So that will determine the microscopic state of the system. On the other hand, when we talk about classical thermodynamics, we know that they don't have the concept of particles or atoms. So in terms of state, they mean that it's the energy associated with the system. And sometimes when we say energy, it's the internal energy. So because we know, later we'll see that internal energy is a state function. So the state of the system will be determined by the internal energy. And the internal energy will be the function of, for instance, the volume of the system, the temperature of the system, et cetera, et cetera. So if you want to describe a state, in the classical thermal, you use internal energy, and it's typically the function of volume of the system and the temperature of the system. So once you know the internal energy, then you probably can determine the volume and the temperature. So those are also the state of the system. That's how you describe how the system is behaving right now. And in the statistical, thermodynamics, we use this configuration, number of configurations to determine the state. And this is also the function of, for instance, internal energy, volume, and temperature. So this is the microscopic view. And this is the, you can say, macro. So depending on how you want to describe the system, in terms of microscopic view or macroscopic view, the state can be described by different functions. So note that when all the properties of a system are fixed, the macroscopic state of a system is fixed, which means that when the configuration here is fixed, the macroscopic properties or macroscopic state of the system is also fixed. So these things are related to each other. And massive knowledge is needed to specify, to determine the microscopic state of a system. Because when we talk about this, we say this is the configuration number of all those particles inside the system. Then we need to know what are the particle configurations like, or the arrangement of those particles. So if that's the case, then we need to understand, or we need to know the information regarding the particle coordinates and also the particle momentums. So if you have a bunch of particles, like 10 to the 23, then you need to know the information of each of them in order to describe the microscopic state. So that's the reason why here it says that massive knowledge is needed because you need a lot of information to determine the microscopic state. The properties of a system will be determined when the microscopic states of the system is known. So that's from the micro point of view. You have to know all the information. Also, it's good that we know that statistical thermodynamics works, but it's also good that we can use classical thermodynamics to deal with some larger systems. Because if the particle numbers is large, it means that it's almost impossible to determine to get all the information from all the particles in the system. So we have to rely on some macroscopic quantities to determine the state of the system. So the bottom line is that when the values of a small number of properties are fixed, then all of the rest are fixed, which means that some of the physical quantities are interlinked. So they are not all of them are independent variables. For instance, we know that for ideal gas, the pressure and the volume are correlated to each other, right? If you increase the pressure, the volume will reduce because P times V is a constant. So P and V are not independent variables. So only one of them should be known in order to determine the state. So that's the reason why over here you'll see that I wrote internal energy as a function of volume and temperature. However, I didn't wrote internal energy as a function of volume, pressure, temperature, what else? Something like this. Because we know that for instance, for an ideal gas, once volume and temperature is fixed, the pressure is also fixed. So we don't need to write this one down. Sorry. Why? So when the values of small number of properties are fixed, which means that, for instance, V and T are fixed, then all the rest are already fixed. Pressure is fixed, internal energy is fixed, and you don't have to worry about anything else. So some of the variables are correlated to each other through some certain type of rules. So consider a simple system that any two properties could be chosen as independent variables. For instance, temperature and pressure. And when temperature and pressure are fixed, the state of the system is fixed. So it's different from what I just showed over here. Here, I mentioned volume and temperature. But in some cases, at least in this example from textbook, it says that the temperature and pressure are fixed. Then the state of the system is also fixed. Because, for instance, like an ideal gas, if you fix temperature and pressure, we know that the volume is also fixed. And so the state is fixed, and all of the other properties have unique values corresponding to this state. So again, the most common example of pure gas system, let's say an ideal gas, the volume can be expressed as the function of pressure and temperature. And this is related to what we mentioned last week. Remember the experiment that a French guy named Monton performed, which results in the Charles law of ideal gas. Right? If you increase the temperature, the volume of the gas will increase. But if you reduce the temperature, the volume of the gas will also decrease. And from that, we can extract a rough estimation of zero temperature. So this is called an equation of state for the system. Again, like for instance here, we can say the internal energy is internal energy as a function of volume and temperature. And this is a very typical expression of the state of the system. Or, for this configuration number, from the statistical point of view, you can say it's a function of internal energy, volume, and temperature. or you can say it's just volume and temperature. It really depends on like how you want to describe it. Okay. So consider a property A. So this can be any kinds of function. For instance, can be u, can be omega, can be v, can be p. And A1 and A2 are the values of A at state 1 and 2. For instance, you have two different states. And they all can be described by this function. And if you still remember from last time when we talked about energy or internal energy, we started from a mechanical analogy, right? We have U1 and U2. For instance, let's say this is time, this is U. So this is U1, this is U2. So we start from perhaps over here, U1, and through time, this internal energy, or let's say potential energy, will increase to a different number, U2. So this property, let's say U, will evolve from state 1 to state 2. Okay? And this process can be either a reversible process or irreversible process. But most of the time, we will focus on a reversible process, as I mentioned earlier. So this quantity, for instance, A, is said to be a state function if the change in the property A is regardless of the transformation linking these two states. That's similar to the case of potential energy under a conservative force system, right? When you move from this height to this height, the change of the potential energy is only related to the height difference between these two states. Okay, it does not matter if you go from here to here like this through path 1 or through, let's say this is path A, this is B, or this is C. It does not really matter. It only matters, what only matters is the difference between these two states, or you can say the height between these two. Because we know that U2 minus U1 will be delta U is, say, AG H. Right? This is H1, this is H2. What only matters is the difference. So this is an example of a state function. That the transformation, the path linking these two states does not matter at all. But if you are talking about, for instance, work, the work done, from here to here or from here to there, if there's some friction, then we know that if the path is longer, then the process will need more work, right? Because you have to overcome the friction, 摩擦力, to get from one state to the other. So the work is not a state function, while the internal energy is a state function. Also, the differential of A, which is represented by dA, as you all learned from calculus, is a perfect differential. If you still remember, typically this state function or this quantity is represented by a function of, say, two independent variables. In this case, A is a function of x and y. So the dA can be decomposed into two parts, which is this is the partial differentiation between a and x, and this a and y, and times dx and times dy, and add them up. So this is basic calculus. And you can separate dA into these two, decompose dA into these two components. And if we further have, if we represent this partial a partial x as a function called L, and partial a partial y as m, if they further satisfies partial partial y equals partial m partial x, then dA is a perfect differential. It seems to be kind of awkward, but this is what you already learned in calculus, right? Because this is remember, these are all, A is a function of x and y, but in this case, we fix y, and in this case, we fix x. So the reason why we have this subscript here means that when we do this partial differentiation, we fix y for this function, right? Okay, this is okay. And so from calculus, we know if this is a perfect differential, we have this, right? So if we fix, so this is this thing over here. So if we take this part and we have the derivative with respect to y, then it should equals to this, and over dx, because we know that there's a interchangeability for this differentiation, right? In the end, these are represented as okay. But this only works when this differential dA is a perfect differential, right? And this is from the textbook. Don't know why it has to write it as L and M, but eventually you'll see that this is pretty straightforward from what you learned back at the freshman year of your calculus. So if this is satisfied, then we say dA is a perfect differential. So for the concept of state, again, we have to restate some of the laws that we've already seen. Boyle's law, like the product between pressure and volume is a constant, which means that pressure will be proportional to the inverse of volume. And so, like I just mentioned, if you increase your pressure, then the volume of the gas will decrease. Right? And if you decrease the pressure, then the volume will be bigger. So the volume will expand. So the relationship between P and V should be pretty straightforward. The product of these two are just a constant. In Charles' law, we've already seen that the volume is proportional to temperature. So from the experiment, we know that there's a slope, right? This is from last time.
This is temperature, this is volume. And we know that there's a certain slope that you can use. And if you extrapolate to zero volume, then you'll get the zero temperature. Right? So this is Charles' law, that volume is a function of temperature and it is proportional to temperature. And it's a linear trend. So if you write it down more carefully, like say stating that volume is a function of pressure and temperature, if the pressure is fixed, of course, because we know that the pressure will affect volume, so the experiment is done at a fixed temperature. Let's say it's at P0, as shown here. Then we change the temperature, right? Let's say here is T0. And here is, let's say, T. But the pressure is fixed. Even at this temperature, the pressure is fixed. Then you can see this linear trend. If the pressure is not fixed, we know that the volume will also change. Right? So this experiment is done at fixed pressure. So that's the reason why at that time when I mentioned the experiment, I said perhaps, let's say this is at 1 atmospheric pressure, for instance, then you have this kind of slope. And if you want to express the difference between these two states, and you want to find a relation between these two states, this is what you will get. Right? The ratio should be a constant, which is the slope of this experimentally determined curve. And this one describes this. This is Joseph Louis Gay-Lussac. It's a law, maybe. It's a derivation from Charles' law that there's a thermal expansion coefficient. And you can see that this coefficient is defined as the partial V, partial T at fixed pressure. So this term over here is the slope of this one. So say the slope over here know that this is partial V, partial T, and the pressure is fixed, right? So we can write it down like this. For instance, at some certain pressure. However, for different kinds of gas, it has a different volume at the standard pressure. So if we want to normalize this factor, we have to divide this slope by a specific volume. Sorry, I shouldn't say specific volume because that's a special term. So by a certain volume, and V0 here is the volume of the gas, of this gas, at this fixed temperature. So we divide, this slope, by this factor, which means that we're normalizing the volume part. Eventually, you'll see that this alpha is 1 over 273.15. Sorry, which means that this is related to the number here, right? If you still remember, we tried to extract this number, and we know that this point is, if this is 0, then this is minus minus 273 degrees Celsius. Okay, so that's the reason why you'll get this slope. And again, this is for ideal gas. This is for ideal gas. So the ideal gas, by definition, is the gas that obeys Boyle's law and Charles' law. So you have to satisfy these two. And that's the reason why if you combine these two, you'll get the famous ideal gas formula. And the ideal gas temperature scale is something like this. So this is from the experiment I mentioned last time, which is a very important experiment in the history of thermodynamics. So combining those two, Charles' law and Boyle's law, you will get this famous ideal gas formula. PV is a constant, and it is related to the temperature. So the higher the temperature, the larger the product between pressure and volume. So these are constants. And typically, we want to set up a standard, like I mentioned earlier, that P0 or P0 is a standard pressure, 1 atmospheric pressure. And T0 or T0 is the standard standard temperature, which is 273 Kelvin. You can say this point. And the volume can be described by or described as a function of temperature and pressure. So volume at some certain temperature and pressure will be fixed. So if you only have the knowledge of temperature, it's not enough to define the volume. You also need the information of pressure. And of course, when dealing with an ideal gas, if you want to know the pressure, you can also express that as a function of volume and temperature. So right now we have this volume, as a function of TMP or TMP. Of course, you can write this as, or we rarely see this one. Temperature is typically something that's already given. So probably we won't see this that often. But we will see these two very frequently because once we know temperature, and if we have some information regarding pressure or volume, then we can determine volume and pressure, respectively. Okay. So from this part, we know that P times V should be a constant when you divide that by temperature. So it turns out that we can have this ideal gas formula, PV equals RT. And this R is what we call the gas constant. And this gas constant will have different numbers depending on the units you're going to use. So this is probably the most important thing for you in this chapter because I believe a lot of definitions are maybe not that important. But if you want to do some calculations, this number is very important. And especially when you are dealing with problems that will give you different units. For instance, let's see this in more detail. I believe most of you have already learned this in the freshman year. If you are using liter ATM per degree mole, then the gas constant is 0.08. And this is because we have PV equals RT, which means that R and this is for 1 mole of gas molecule. So in fact, there's a factor of N that is being neglected here, or the famous PV equals nRT. And N equals to 1 in this expression here. So it is the gas constant per mole. So that's the reason why we have mole over here. And so let us put this here. So the unit, let's say, or the dimension of it is the dimension of P, V, and T. This bracket here means that we're going to extract the unit or the dimension of that physical quantity. For instance, in this case, for pressure, let's say for pressure, we have ATM here. And for volume, we have liter, right? Liter at ATM. And here is the temperature. We have, let's say, degree. And the degree here means Kelvin. So it's degree Kelvin. And here is mole, right? So it turns out that the most straightforward expression will be liter at ATM degree mole for its unit. And the number, this is from the experiment, right? It's 0.082. However, it turns out that the product of pressure and volume is also in the unit of energy, right? If you still remember from, I don't know, maybe a general physics course, that work is, later we'll see this as well, is P dot dV, right? And then there's integration from volume 1 to volume 2. So it means that the unit of work, we know that this is energy. Should be the same as a product of PMV. So though here we are using liter ATM, but if we're using SI unit, which is the standard unit system, then P times V will give you the dimension of an energy, which is, this is joule, right? How much energy you have. So P times V, it turns out that it's also joules. But in order to convert, from liter ATM to joules, you have to use there's a conversion ratio. But the bottom line is that if you use joules as your unit over here, for the top, then you have to use a different number. So always remember that look into the problems carefully to see what the problem tells you. And if it gives you in units of liter dot ATM, or at the beginning, the information of the volume and the pressure they give you is in units of liter and ATM. Once you have the results, and if you want to convert that into energy, you have to take into account the ratio between these two numbers, right? Because they are in different units. And of course, we know that joules can be converted into calories. That conversion is from the experiment done by Joule himself, right? How you measure heat and how much can be converted into work. So cal is having the same dimension as joules, just the measure is different. So 1 cal is like 4 point something, 4.18, right, joules? So this is like roughly 4 times this number, right? Because 1 cal is roughly, I think, 4.18. So we can do the conversion from here to there. It shouldn't be that hard. So these are the numbers that you will encounter when you try to calculate using this gas constant. You have to be careful which one you're using. But the bottom line is that the gas constant has these 3 different representations. So another definitions. Extensive and intensive properties. These are pretty straightforward. Extensive means that that value of the property depends on the size of the system. For instance, like volume and mass. Because we know that if you have a larger volume, it means that the system size is bigger. So it's an extensive property. And mass as well. As you add more particles into the system, the mass will increase. On the contrary, you have these called intensive properties. And those are the values that are independent of the size of the system. For instance, temperature, pressure, specific volume, and molar volume. It means that the size effect has already been normalized. If you still remember, when we talk about this factor, we know that this alpha, this constant, should be an intensive property, right? Because we've already normalized this factor by its original volume. So we already take that size effect into account, which means that, anything that is related to like specific something, like specific volume, specific heat, or something molar, molar volume, what else? Like molar mass. Those things are intensive properties because it does not depend on the size of the system. Okay. But I guess the most important intensive properties are like temperature and pressure. Okay. For instance, if I ask you if internal energy, is it a extensive or intensive properties? It should be pretty straightforward, right? Because we know that, for instance, for ideal gas, the representation of internal energy is something like this. Temperature is intensive. This is a constant, so we don't have to worry about that. However, the number of the particle is an extensive property. Therefore, the internal energy should be an extensive property of the system, right? So therefore, this is extensive. Okay. So if something is related to the size of the system, then it's an extensive property. Okay, phase. The constitution or phase diagram as a diagram represents the equilibrium states of a system. So I don't think we have to explain that verbally. Later we'll see some examples. And the component from its definition is a chemical species of fixed composition. So for instance, when you're dealing with just I think the example, maybe the best example is if you're dealing with just one kind of metal, let's say gold, if you have a piece of gold, then you only have just one component in your system, right? Because if you have a piece of gold, within this boundary, you all have just gold atoms. So this is a one component system. Because you only have one chemical species. However, if you started doping some of your gold piece, for instance, I want to dope copper into your gold, which is a very common binary alloy, right? If you have gold and copper, or sometimes you can say gold, let's say 1 minus X, and copper X. If you start doping copper into gold, you'll get a better mechanical properties from this material. And at the same time, you start to have two components. So it will become a two-component system. So these are just some definitions of terms when we want to describe like what our system is. And for instance, one component, unary. Two components will be a binary system, ternary, quaternary. It depends on how many chemical species are involved in your system. However, phase is a different concept. Phase and component are two different concepts. Phase means that there's a clear part, a certain part of the system are having an equilibrium state. So that's the reason why here we say that phase diagram means that a diagram represents the equilibrium states of a system. One example, like you can melt the gold or melt this gold-copper alloy into liquid. Then the phase will be different, but the components in the system are still the same thing. We're still having gold and copper, it's just the phase is different. Another example, for instance, for one component system is water. And I believe most of you already know this. We have this, we call this three-phase diagram, right? And we have the solid as ice, liquid as water, and vapor as water vapor. And this is the one atmospheric pressure. So we know that if we go from negative to positive temperature, degrees Celsius, ice will be converted into water. And at 100 degrees Celsius, it will be converted into gas. So there's nothing special here. And there's a point at which three phases are in contact with each other. So if you're in this point, for a certain temperature and a certain pressure, then these three phases can coexist, right? And this is a very typical example of phase diagram, that you plot the phases, on a plot with two axes, and one of them is typically temperature, and the other is pressure. Of course, these are not restricted to pressure and temperature. This is another example. Another example of helium. You have the phase diagram similar to that of water. Again, this is one component. You have helium, and this is the pressure axis, and this is the temperature axis. And we know that in order to liquefy helium, you have to go down to, say, 4.2 Kelvin at 1 atm. So this around here, you can draw a line, and you can see that the point will, intersect with this boundary at about 4 Kelvin. So that's the point where helium gas will become liquid helium. And of course, you can go further down and you will start to see different phases of helium. So these phases, although they are all liquids, for instance, you have liquid helium-2, liquid helium-1, they are all liquids, but they have different, let's say, physical behaviors. So we'll categorize them into 2 different phases. Okay? And like I mentioned, it's not just the temperature and pressure. You can have temperature and also the percentage. If you have 2 components, for instance, if you're dealing with this kind of, let's say, alloy, then you can have 2 components. And depending on the relative composition of these 2 components, then you can have different kinds of phases. And of course, if you raise the temperature, these will become liquids. And if you go down to lower temperature, there's some certain temperature range that you will get phase separations. Right? These 2 components will start to separate. However, if you cool further down, they will become just one single solid phase. I believe that you've learned this in the materials, introduction to materials, science, engineering, and also for the next semester of thermodynamics of materials, you'll see this kind, like how we calculate this from thermodynamics. And there are some more complicated phase diagram. I believe you've already seen this before. And there are other types. For instance, if you're talking about the phase change of a superconductor. So this is a different kind of phase transformation, which involves no latent heat. And so this is a different kind of phase change, unlike the water to vapor or the water to ice phase transition. But you can change the temperature, you can change the magnetic field, and you can also change the phase of superconductors. There are just some other examples for some modern condensed matter physics. So by changing doping, you can also change the materials from, say, antiferromagnetic states to superconducting states, or to just a normal metal. So you'll see all kinds of phase diagrams in the future when you keep further studying. So these are just some final notes. Phase has a finite volume in a physical system, and the properties are uniformly constant within this boundary. That's how we define phase. And they are macroscopically homogeneous body of matter, and the phases of a system can be physically separated. For instance, water and ice, they have very clear boundary between them. And a phase has a different composition or structure from that of the other phase. For instance, water and ice, they have different structures, right? Ice has a certain kind of crystal structure, but water, it doesn't have any crystal structure. So that's what this slide is about. So we'll take a rest and we'll come back later. So, I mean, a phase has a different composition from the structure of the other phase. So that's the reason why when we talk about phases, they will introduce 2 terms, which is, first of all, homogeneous. Homogeneous means that it is, within any of the one phase areas in the phase diagram. So if you're talking about, for instance, the most common case like water, we'll say that if your temperature and pressure is, say, over here, then your phase will be a uniform or, say, homogeneous liquid phase. However, if you're at this point, We know that when you put ice into water, and if you fix that at 0 temperature, these two things can coexist. Although it's the same component, but the phases are different. So under that circumstances, we'll say the system is heterogeneous, because we have more than one, so 2 or more phases in that kind of situation. So as long as you're at the, let's say, the boundary of a phase, for instance, we're at here, we have some certain doping, and we have a temperature right at the boundary, such that the state is at this boundary, then we know that, for instance, superconductor and this Fermi liquid phase can coexist, and the system will become heterogeneous, because those two things are happening in the same place. But if you move to this area, if your temperature is, say, lower, and your doping is, say, right here, you're within this boundary, then the system will have only one phase. Then you have a homogeneous situation. Okay, so these are just some terms that we have to go through in order to let you understand of what the textbooks are talking about, but especially for this textbook. And the chapter 2 of this book is, again, it starts from the first law of thermodynamics. So basically, for this book, it doesn't spend too much time on, say, the 0th law of thermodynamics, which is related to the definition of the temperature I mentioned last time. So it goes straight to the first law of thermodynamics, which is, again, this formula. And we've already seen this many, many times. So I guess I don't have to spend too much time on this. So again, just by changing the the order a little bit, but of course, I prefer putting delta Q on one, for instance, on the left-hand side, and the sum of du and delta W on one, on the right-hand side, such that it's much easier and there's no minus sign involved. But in this case, of course, this is what the textbook has. So the notation is a little bit different. Again, and also they use small q and small w and small delta, but typically I prefer this. Again, and if we move it, this will be something like this. And again, internal energy change is related to the heat flow into the system and the work acting on or done by the system. So again, internal energy and heat exchange. So if this number is positive, it means that heat flows into the system, right? Because it flows into the system, then the internal energy will increase. And if you have a positive work, it means that work done by the system. If this is positive, it means that you have a minus sign here, right? So the internal energy will decrease. This makes sense, right? Because if you have work, let's say, work done by the system means that the system is doing some work to the surrounding. So if this is positive, it means that the internal energy will decrease, right? If this is positive, internal energy will decrease because you are losing energy and you are doing something to outside. Okay? So this is the definition of this book. And if it's negative, it means that the work is done on the system. We're doing something and increasing the internal energy of the system. So that's the reason why we have this. And this is another expression I took from the internet, that the change of internal energy is heat added to the system minus the work done by the system. So this is more straightforward. I believe that if you can remember this, you don't have to worry about the definition from the book. That if you have input from outside, this is positive, then the internal energy will increase. If you are doing some work to outside, then this will decrease the internal energy of the system. However, if you are doing something, you are sending work into the system, the work is done to the system, then there's a minus sign going in, so it's a negative number, and this will become positive. Overall, this will become positive, and the internal energy will increase. So just think of it as some energy transfer between the surrounding and the system, right? So this shouldn't be that hard to understand. And U is the internal energy of the system. That is the pertinent function describing the state of the system. So we've already mentioned this, go through this several times, that U is a state function. So, or the change in the state when the potential and kinetic energy of the system are fixed at a constant. So so that's the reason why typically when I talk about internal energy, I use the analogy of a mechanical system, and I use potential energy to describe it. But of course, if you're dealing with ideal gas system, for instance, gas molecules, the internal energy is the sum of the kinetic energies of all the gas particles in the system. So you can say that it's the total energy, including potential and kinetic energy of the system. And a small change of internal energy, du, is a perfect differential. Therefore, if you do a cyclic integration of that quantity, then it's 0. This is also pretty straightforward because, again, we have state, let's say state A and B. And imagine that we have two paths. We know that, say, this is U, this one has UA, this one has UB. And we know that this delta U is constant, right? For path A, for path 1 and 2. The difference will be the same, which means that let's say A to B, let's say it is delta U, then will be minus delta U, right? Because it's the opposite. UB to A will be UA minus UB. So it's the opposite of delta U. So if you add these two together, well, it should be 0. Right? This is pretty straightforward because it is a perfect differential. So if you go from here to there and then go back to its original position, then the change of the internal energy should be always 0. With that information, and for the first law, then you know that the change of heat equals to the change of work when you perform this cyclic, let's say cyclic process. We know that when you go from, say, A to B, the work done by the system will be different depending on the path. So from here to there, let's say delta U is constant. But if we're talking about the change of heat and the change of work, let's say the change of work from here to there, let's say the delta W A to B will be different from the work from B to it. Sorry, this is path 1. So you know that, from here to there, the work done by the system will be different. Although the state, the initial state and the final states are the same, but the work will be different. For instance, if we're dealing with a PV plot, if you still remember, when we talk about this plot before, the work, let's say dW is P dV, right? And so the work difference will be the integral of P over dV from, say, volume, let's say A to volume B. Let's say here we have volume A, and here we have volume B. From this state to this state. And the initial volume is VA, is smaller, and when we go from here to there, there's a larger volume like VB. And this pressure is represented by the value along this horizontal axis. So the pressure will go up in this case and then go back down. For path 2, it will go down first and then it will go back up. So the path will be different. So if you try to calculate this, this number, it will be different for the two cases, right? Because for path 1, is some certain number. For path 2, we have a different dependence of pressure as a function of volume. And these two numbers are not the same, right? This number and this number. And we can clearly see that the work done by the system for path 1 is greater than path 2 because this is the area underneath this curve, right? This part. So this is let's say a shape like this. While for this one, we go from here and then to B. So the shape is something like this one. So you'll see that this should be much larger, not much larger, but this one is larger than the volume beneath path 2. So, sorry, not volume, but area. But anyway, it's obvious that the work done by the system, if you follow path 1, will be greater than that following path 2. So, again, for this example. But we know that the internal energy change is the same because internal energy is a state function. And if you know first law, so for first law, it states that it states like something like this, right? For path 1, you can write it down like this. And for path 2, you can write the same thing. And we already know that these two are the same. Right? These two are the same. So we don't have to worry about that too. And this one is greater than this one. So it means that delta Q1 will be greater than delta Q2. So during this process, the heat exchange for path 1 will be greater than that from path 2. And we know that since these two are the same, so these two will be the same. So that's the reason why when you do the cyclic process, if this is 0, right, then the integration of a cyclic process over delta Q will be the same as the cyclic integration over delta W. So it's all based on, at least this one, it's all based on the first law of thermodynamics over here. So this is a very standard example of looking at processes. So it's typically a PV plot. It's a pressure versus volume plot. And the work done by the system is the area underneath the path. So this is the expression or the formula that we use to calculate the work done by the system. Okay. So it means that the first law originally is something like this. But typically, later you'll see expressions like this. Because the work is typically in the PDV form. Typically for a reversible process, you can do the calculation like this. And a physical meaning for that is we know that, what is the physical meaning? Well, imagine that, again, you have a cylinder and you have a piston here, and you have some weight over here, and this is the volume you have. And if you want to keep the pressure as a constant, but at the same time you expand the, the volume, you move this thing up. So the volume was expanded from original volume V to V plus dV. So you have an increase of volume called dV. And the work done by the system, to this weight, to lift it up, can be expressed as PdV. And the reason why this is the case is because, for instance, in this case, dV is let's say h. So the height, dV here means the volume. But the lateral motion along z-axis, let's say dH, which is the height difference. And if you want to calculate the volume, dV, it's A times dH, where A is the area of this piston. Because if you, let's have a 3D plot, then it's something like this, right? And this one has some certain volume, certain area, we call it A. And we have some certain pressure. So if we fix the pressure, and if the volume has been expanded, then the work done is P times A dot dH. And we know that this is force, right? So essentially, this is the same as the mechanical work. The definition of mechanical work, right? The mechanical work is defined as the inner product between the force and the change of coordinate. So it depends on, like how you move your sample, so how you move your object. And so here, we're moving this thing up by expanding the volume of the gas. So eventually, this is what you will get. Like this is the force, and the distance of the motion from here to there. And the force can be decomposed into the product between pressure and area, right? The area of the piston. And then A times dH is actually the change of volume, dV. So essentially, these two are the same. And so this is the origin of the PdV work. But the bottom line is that the first law sometimes can be expressed like this. And for a system that is simple, consisting of a given amount of substances of fixed composition, and the value of U is fixed once any two properties are fixed. So we've already mentioned this several times, that typically we will pick two variables as the independent variables to describe the system. So if these two are fixed, then the system is already fixed. The state is fixed. So for instance, V and T, volume and temperature, are chosen as the independent variables. Then the internal energy can be expressed by or as a function of volume and temperature. And similar to what we've seen earlier, we use the example of an arbitrary function A. Here we use U, then it can be decomposed into two parts. One is related to dV, one is to dt. So please remember this, because this is very important for what we're going to talk about. Okay, you can decompose du into two parts. One is related to partial U, partial V at fixed temperature, and the other is partial U, partial T at fixed volume. So I've already mentioned this. Delta Q and delta W are not state functions, and they depend on the paths linking the initial and final states. Like I just, sorry, I erased it, but you've already seen that. Depending on the path, you will get different numbers in terms of work. So based on first law, you'll also get different numbers for the heat exchange in and out of the system. Because for state 1 and state 2, we know that delta U will be the same for these three paths, but apparently the work will be very different. Right? For instance, in this case, similar to what I showed earlier, if you go through path A, then the work done by the system is larger than if you go through path C, because the area underneath this PV plot, or underneath this path, is smaller for path C while compared to path A. So that will also affect the heat transfer between the system and the surrounding. So I think this is probably the example shown in the textbook. I'm not sure if it's in the 6th edition, but I think it's probably in the 5th edition. So this is a very typical PV plot that you will encounter for the first two chapters, because it will describe the process. And there are many different kinds of processes, and we typically will categorize them into, I would say, 3 or 4 types. The first one is called isobaric, or the constant pressure process. For a constant pressure process, it means that on the PV plot, the pressure is constant, and therefore it's a flat line. So it will just go from, say, state 1 to state 2 with a fixed pressure. Okay, the P external here, or P exertion, is a constant. So it's independent of the volume. So although you have the expansion of volume from 1 to 2, but if the pressure is fixed, then we know that the work done by the system is very simple, right? It's just area underneath. So the work, so the small w here is the expression from the textbook, but I typically prefer like delta W is, again, PdV from V1 to V2. And P is a constant, so let's just write it like this. Therefore, the integration is very simple. It's just a product between P and the difference between V2 and V1. So this is pretty straightforward. And let us assume that delta Q, in this case, is represented by this QP here at constant pressure. Then from first law, we know that the difference of internal energy between state 2 and state 1 is the heat involved here minus the work done by the system. Right? Or if you want to write it in a reverse way, like I mentioned here, then this will just turn into, let's say QP is U2 minus U1 plus P V2 minus V1. Right? It should be something like this, which is the same as here. Therefore, if you can rearrange that a little bit for something that is purely related to state 2 and things that are related to state 1, if you rearrange that, you'll get something like this, which is the same as what the textbook has. And therefore, we can define a new function called U plus PV as our new state function. If you're going through an isobaric process or constant pressure process, you can define H as U plus PV, and this is enthalpy. Let's say this is H2 minus H1, right? So it turns out that the definition of H is U plus PV. And this thing is called enthalpy. Chinese is Han. So when people are talking about constant pressure process, then you know that, okay, you're going to use enthalpy as a measure of the change of heat, right? Because this is QP. So again, this is the enthalpy of a system. It's a state function, and H2 minus H1, the change of enthalpy will be the heat change of the system. So this equation indicates that enthalpy change during a constant pressure process is equal to the heat emitted to or withdrawn from the system during the process. Okay, so what does this mean? It means that this is a good measure, the enthalpy as a new kind of function is a good measure to estimate how much heat is being transferred into or out of the system when you're dealing with a constant pressure process. So again, if you recall that last week we talked about enthalpy as a way to calculate things. And the reason why we need enthalpy, at least from Peter Atkin's book, is that, let me wipe this up. When we're dealing with combustion, typically we fix the pressure, which means that the volume is free to grow. Like we have fuel. So we burn some fuel here, and eventually, things will start to, let's say, evaporate, and therefore, those molecules originally in the liquid will start to get into the gaseous form. So they will become gas, and the volume will expand. However, there's no restriction of that expansion. Therefore, it means that the pressure is fixed at some certain value. For instance, the pressure is at 1 atm, but the volume can change. So in order to estimate how much heat, let's say, is going into the system, we have to estimate that by not only the change of internal energy, but also the expansion part. Right? We know that if we heat up this fuel, the internal energy of the fuel will increase. But at the same time, we also have this expansion of gas. So not only this should be taken into account, but also this part. And that's the reason why we have to use enthalpy as our measure of the heat exchange. However, if we're dealing with other types of processes, for instance, isometric or constant volume process, it means that there's no change in terms of volume. Then the PdV work should be 0, right? Because dV is 0, so there's no work, no PdV work. So 2.1, equation 2.1b, let's go back to that. I don't know where. So this one, since we don't have the PdV work, this will reduce to just du equals d delta q, which means that if you fix the volume, right, and if you send heat into the system, that heat will be completely turned into the change of internal energy, right? Because the heat being sent into the fuel will no longer do this extra work because the volume is not free to expand. So in the constant volume case, the delta Q will be just delta W because PdV work is 0. It's pretty straightforward if you just write that. If you just use this, right? Because volume change is 0, so eventually dq is du. So in this textbook, it states that the change of internal energy is the change of heat, but it has a subscript v to represent that this is different from the heat when you have the heat change that you will get when you have a constant pressure process. This is for the constant volume process. The change of that will be identical to the change of internal energy. And there's another process called adiabatic, which means that there's no heat exchange. Therefore, dq is 0. So again, if you look at this, first law, dq is 0 for the adiabatic process, then the change of internal energy will be related to the work done by the system. Right? If you, an example that I already mentioned last week is that if there's no heat exchange, right, and if your system do some work to the surrounding, then your system will lose internal energy. Right? So if this is increasing, then this is decreasing. Okay? So this is for the adiabatic process. But I think the most important thing is to understand what these terms mean. So especially when a question tells you that so this system is undergoing a adiabatic process, then you have to quickly understand that we have to use this equation, we have to use this formula, and then we have to set this to 0 because there's no heat exchange for adiabatic process. And if you're dealing with isometric, then this part is 0. And if you're dealing with, say, the isobaric, the constant pressure process, then you have to use enthalpy as your account for the heat change. Okay. And the last one is isothermal. Isothermal means that the temperature is constant. So it's hard to see from here, like how we can play with first law. But it turns out that, for instance, for ideal gas, if your temperature is constant, then the internal energy change is 0, right? If you still remember. For ideal gas, right? So if this is 0, then the change of internal energy is 0. So for isothermal process, and if you're dealing with ideal gas, then du is 0. But again, this is for ideal gas. This is for ideal gas. If you are dealing with some other system, this is not necessarily true. Okay, so isothermal, T is constant, du is 0. So if you use this first law, you'll see that for isothermal process, the heat will be directly converted into work. There's no change in terms of internal energy. Okay, so these are some constraints for the processes. And if you plot them out on this PV plot, you'll see that for isobaric or constant pressure process, this is just going through this horizontal line. And again, iso volume or isometric, it's just going downward. So there's no change in terms of volume. So PDV work is 0. And the heat will be directly converted to the change of internal energy. And for isothermal, temperature is constant. And you already know this curve, right? Because for isothermal, if you use the ideal gas law, which means that this is constant, and if the temperature is fixed, we know that P times V is a constant. So that's the reason why you have this trend in terms of the PV line. And for adiabatic, the line is a little bit different, which is the focus of the next few slides, I think, to talk about like how we deal with the adiabatic process. Okay, the line is a little bit different, but I believe that I think probably they taught this in the chemistry course already, right? Like how you derive this adiabatic curve. But this is sort of the most important thing for the first chapter of thermodynamics. Another quantity that we have to define is heat capacity. It's also stated originally in last week's lecture that heat capacity is the ratio of heat added to or withdrawn from the system to the resultant change in terms of the temperature, right? And typically, if you want just to write it down, it's defined as Q over delta T, or you can say delta Q over dt. Depends on like how you want to write it down. But the definition is very straightforward. It's the heat transfer over the temperature change. So I won't go into details again, but this is the definition. As defined will be infinite when phase transformation occurs. The reason why this will become infinity, or you can say will go to infinity when there's a phase transition is because during phase transition there's no temperature change, right? This is something you learn in general chemistry, that there's something called latent heat, right? For phase transformation, delta T is 0. So you keep dumping heat into the system, right, when you try to melt an ice. But as long as the ice is still there, is still undergoing this phase transition to water, the temperature won't rise, right? So it means that during the phase transition, delta Q is, this is finite, but delta T is 0. So if you use the definition of delta Q over delta T, then this will go to infinity. So there's a singularity of heat capacity during phase transition. Okay, this is another interesting remark on the heat capacity. But once the phase is fully converted into the final state, then this will become finite again, because when you keep dumping heat into the system, the temperature of the system will start to increase. So if a system is in state 1 and the absorption of a certain quantity of heat by the system increases, its temperature from T1 to T2, then the statement that final temperature is T2 is insufficient to determine the final state of the system. It means that, like, when we say the final state is at some certain temperature, it's not sufficient to describe the state of it. It is very straightforward, because if you go to this plot, let's say that the temperature here is some certain value. It is possible that there's another point over here will have the exact same temperature. So this is, well, it's not necessarily describing the state of the system. If the problem or the statement just give you the temperature, you have to need some other variables in order to accurately determine the final state, or the initial state. So here are just some other definitions for heat capacity. There's a heat capacity for constant volume process, heat capacity for constant pressure, and it's all based on what we just saw earlier, that the delta Q will be du for the constant volume. So it turns out that you can write du as Cv times dt. And Cp means that the constant pressure heat capacity, and we know that delta Q is dH in this case. So dH is Cp times dt. And these are all extensive properties, because it depends on the size of the system. So we'll stop at here, and next time we'll start to look into some more complicated derivations. Okay.